Good evening. Are we missing people? We're missing.
There's more room to it.
We're missing two for now. So how's everyone doing? Our classes tired the second week.
I'm done. I'm dropping out.
You missed the free dropout. I have to pay half.
Yeah.
And I think last Monday was the last day for unrestricted drop.
Well,
Just stick around. So, last time we were talking about what? Not yet. Registers, bringing stuff to the CPU, main memory, how to bring stuff from into the memory, whatever. Any question on that? Any concerns? Well, you have to remember it because tomorrow that's what you'll be doing in the lab, in addition of what you'll be learning tonight. So we've learned about main memory and how to access it, how it works, why we need main memory, correct? Because many programs, many algorithms that you need to implement will need more than just registers. Do you agree? Sometimes you have to process images. That could be a few kilobytes. You have to process a lot of numbers that will not fit in the register. You have to actually have a bigger storage space you can work with. Make sense? So now what about input-output devices? So how do you interface with I/O devices? The bus has something to do with it. But there are two major ideas on how CPUs can access I/O devices. These two paradigms are the memory mapped I/O and using I/O instructions to use I/O devices. What do you think a memory mapped I/O is? Can you give me some ideas of how memory mapped I/O is accessed by the programmer?
You're talking about like an external flash card or something?
Whatever, any I/O devices. LEDs and switches that you saw in the lab last week. That's memory mapped. So from the programmer's perspective, how do they look like?
Look like a memory address.
Looks like memory address. Does that make sense? So all these I/O devices have their own registers, not the CPU registers. Their own registers that actually manifest as the state of that I/O device. For example, the LEDs, when you write a number, it'll display those numbers, that number, as an array of LEDs, right? But from the programmer's perspective, it's just some memory location there. Does that make sense? Now, LEDs and switches are pretty simple. They're basically just input and output pins that you can either drive if it's output pins like LEDs, or you read from if they are switches. Correct? But you will encounter more sophisticated I/O devices that may need tens of registers to interface with. Things like USB, right? The keyboard has a USB interface. It does have a computer and a keyboard itself, a controller, microcontroller. There you have plenty of registers you have to work with. And it's still memory address. Does that make sense? Now, when your Windows crashed, and you see blue screen, sometimes if it's crashed by a video card, it shows some memory locations. That might be the video card registers. Right? Even on a computer like a laptop, your desktop computer, it's still the same concept. It's just hidden from you. When you program little microcontrollers like Atmel, PICs, it's more obvious. Like let's say I want to change the setting of that port, then you write to this address for that control register for that I/O device. Make sense? Now the other way that the CPU designers can use are to actually introduce I/O instructions. So now the programmers use different instructions for accessing data in memory or trying to interface with an I/O device. Does that make sense? So you actually have to use separate set of instructions to deal with I/O. With memory map, everything looks like memory, but from the programmer's perspective. So you're just given a location. Hey, that's the register for this I/O device. When you write to this is what happens. So if you are programming a microcontroller and you go through the data sheet, the manual, it tells you all the details of how to interface with certain features of the microcontroller. Let's say you want to do CAN bus. It has a set of registers that you have to use. Serial communication. You'll see even PLP CPU, which has a serial communication port. How to interface with it with memory map I/O. Cool? You'll see this more later. So the pros and cons for memory map. So I/O control registers look like memory. So easy. You don't have to learn more instructions. It just looks like it's over there. I just have to change the address. It simplifies the CPU hardware because it doesn't have to support more instructions. It just, for example, for PLP CPU, it just needs float word, store word. With just those two instructions, you can access main memory and all the other kind of I/O devices. That really simplifies the CPU. But the cons are it consumes address space, right? With 32-bit system, you have 4 billion possible combinations to address things. If some of them are used by I/O devices, then those combination of bits are lost to address memory. Does that make sense? So some of those cannot be used to access memory. So for example, let's say you have an 8-bit CPU. How many possible addresses you can access? 8 bits, 256. Let's say you have I/O devices that take 30 of that address space. Now you cannot access more than, what, 226 address spaces. So you can't have RAM that big now because that space is taken by I/O. Does that make sense? It's not a problem with general purpose computers because you have 64-bit address space. 4 billion times 4 billion. Like if few hundreds are being used by I/O, who cares? Right. So same reason why on 32-bit systems you can't really access the whole 4 gigs. Have you ever had use a 32-bit Windows and you have 4 gigs of RAM? You don't see the whole 4 gigs because the kernel, the operating system, reserves some of that space for other things. Any question? For the pros and cons for I/O instructions, the cons require special instructions and requires additional complexity. But the pros will be you have the whole address space. So this is an example of how a memory mapped I/O may look like. This is the CPU with the 2 buses. So the instruction bus is hooked up directly to the memory because it doesn't need to share because it uses that bus all the time. That's the reason why we have split bus. And then the data bus will have to go this thing called the bus arbiter. Have you ever heard the term soft bridge on your CPU, on your computer? So you missed out the PC building scene in the 2000s, early 2000s? Now everybody has just a laptop. Yeah, it's like a controller. That's basically what it does. It interfaces the CPU with the rest of the motherboard. Interface with the video card, the USB controller, everything, right? So it shares, the bus gets shared. Cool? So the same thing here. So you have the data bus that connects to main memory, and then you have the arbiter that selects which way to go depending on what address you give it. For example, let's say you have this memory map. For this kind of system, if you do a load word in this range, the bus arbiter will route your request to this guy, to this port. If it's within this range, it'll route it here and let the bus interface of the I/O device deal with it. Does that make sense? Any question? So from your perspective, IO looks like a what?
Memory.
Memory, just memory. It's just that when you go higher level, oh, but that location has special meaning for that IO device. Right. When you go out there and you actually program microcontrollers, this is all abstracted. So you can name memory locations. It's called labeling. You can label memory locations, so you don't have to remember the hex combination. Right. So you actually can, when you actually program, you don't really type in the memory location. You can look at the datasheet and see where the registers are for the I/O, but usually the vendors of the microcontrollers abstract it away. Right? So when you program in C or even in assembly, you don't have to remember the actual address. You can just load from control register to 1, something like that. You'll see this a lot. So the simplest example would be switches and LEDs, right? So let's do this in PLP tool and see how switches and LED works. You kind of saw it in the lab last week. Let's revisit that as soon as Java loads. Oh, that was quick. So it's too small. So this is your program. It starts. So as I said before in the lab, what does this mean? So you're telling the assembler to place everything after the statement in that address, which is the beginning of your main memory in PLP-CPU. Cool. So where is the LED and the switches? Where are they? In memory map. How are they mapped in PLP-CPU? Yeah, so the quick reference tell you where things are. So switches is in F010 zeros. LEDs is in F02 all zeros. Right. So let's load those addresses to. So this is my switches, right? So this is, you're loading the pointer to where the LEDs and switches are. Now we want, for a simple example, we want to read from the switches and write to the LEDs, just to echo whatever the switches are representing. So how do we do that? What instruction do we use to actually load word? What's the first register? What's the first operand? The target. And then how do you actually use the pointer? The offset, and then whatever is in register 1. So there's some indirection here. This is why I wish everybody learned C when they take their first programming language. Because so many concepts in C that translate directly to low level, because C is pretty low level. Java hides memory management from you, right? C doesn't. So when I say pointer, if you know C, you'll know, oh, it's in direction. So I'm actually not writing to that. I'm writing to or reading from what it's showing, telling me what, pointing me at. Does that make sense? So these two registers are holding a pointer, because you don't use them directly. You just use them to point you to at the real location of the data. Make sense? Now, after this statement is executed, you'll have whatever the switches values are to register 3. Now we want to copy that to what? So what do we use? How do we output through the bus? What's the store word? Right? Now, store word is weird because the first register usually is the target, but store word, the first register is the source. Right? So we use the third register again, and then use the same address. Oh, let's see if this works.
So if the load word first, or the first position is the target in the syntax, and the store word the first position is the what?
The source. So you use the contents of this register to be written to be stored to whatever this thing is pointing at.
Wouldn't we want to store it in reg 2? Isn't that reading from the switches and storing it right back to
Good.
the switches?
This is incorrect. You paid attention. What is this doing?
Sending it back
To switches. On a typical microcontroller, when you try to write to an input, it will not manifest on the output. So yes, you are correct. This is a wrong program. You want to write to the yes. Now let's see if this works. It wouldn't have. So I will bring up the switches. Bring up the. So let's say we want to flip those switches. We execute. So now we have all the addresses. So if you go to the watch window, you can see so the two registers are now holding the addresses, right? And if we execute the load word, the third register has the value of the switch, which is hex 91. Right? This is 9, and this is 1 hex. See that? Because the switches are binary, and each 4 binary digits is a single hex digit. Right? So this 4 digits is 1 in hex, and these 4 digits are 9. You see that? Because this is 1, 2, 4, 8. So 8 plus 1 is 9. That's why we use hex. Otherwise, it's a pain because you have to parse through all these ones and zeros. So at least it makes it a bit more readable to us. Now, after store word, what do you expect to happen? So now the LEDs register see that value and I need to actually drive these pins, and that makes the LEDs light up. Question? So load word, store word, you'll see that a lot. And in other architectures, if you use MIPS, it will look like this exactly. If you use something like Atmel or PIC, there are other addressing modes, but you have to be able to distinguish when you're trying to access registers like CPU registers or I/O memory, right? Have that blocks, the CPU blocks in mind when you program. Like, am I accessing memory or am I accessing registers? Or things like that. Cool. And it'll get even more confusing because some architectures allow you to do operations on non-CPU registers. PLP-CPU is strict. If you want to do operation, you have to bring the value into your CPU data registers, right? Explicitly. You have to load it first, load the values first, and then do operations. Some other architectures allow you to actually, okay, the first value is from this register, second value, take it from memory. Motorola allows you to do that. So be careful. So make sure you know the architecture before you program it. Now, if you haven't noticed, the only thing CPU has been executing is just sequential programs. You think that's how it works? Just execute once, and if you fall off, you're done. Think of the devices that you've been using. There's the fridge just run once, like do the code once and then just stop working.
life cycle? Has it died yet?
Really, really slow execution, just like, execute now. No, right? It keeps on running. And depending on your input, you might change some knobs. It changes the operation. It may change the temperature. It may change the light, whatever. So that implies a what? Loop. What is a loop?
Just repeating the same thing over and over and over again.
Repeat, right? So you execute parts of a program repeatedly. Do you see this in C?
Yes.
Where? How?
For loops.
For loops. While, do while. Right? So you have a portion of your code that you execute repeatedly. Why? Why don't you just write it up?
So it's constant.
Since it's not going to be repetitive, super repetitive.
Good for your, bad for your wrist, right? What about in terms of the program space, right? You may have a huge, you have this huge code that you execute repeatedly. Like if you unroll it and if you write it out, it'll take more space in your memory, right? So there are ways. Make it easier to write code too, so you don't have to actually have to do this again. Control C, Control V, Control C, Control V. So it makes sense to have constructs like loops. So the first control structure we have is the jump instruction. So with the jump instruction, you unconditionally jump. So when the CPU sees this instruction, it'll immediately, oh, I have to go here. No conditions. So you just do it and jump to wherever you tell it to jump. Let's revisit our program here. Let's say we want to make this program execute indefinitely. So we can have a label here. Now instead of just falling off the end of the world, here we can tell the CPU to, hey, jump back. Well, let's see what happens now.
You're told to jump back to the start of the loop.
Yes, to where the label is.
So J is the instruction itself. You could have put drool up there and put J drool, and it would go. Doesn't have to be the syntax.
Well, the label needs to exist, right? If you do J drool and you don't have drool anywhere.
That's what I'm saying. If you change loop in both places, if you did a find and replace loop to drool, it would still function.
Yes.
So it's not syntactically required to say loop.
No. It's just an identifier.
What is the meaning of the MLP? Yeah.
Good question. So in the MIPS or PLP architecture, when you do a jump or a branch, the instruction right after it gets executed too, by design. Right now, that's all you need to know. Right? If you don't have anything useful to put in there, just do a no-op. No-op means no operation. So when the CPU says no-op, it says, okay, I just jumped. Right? When you take compart, you'll see why that thing is there, and that is by design. For you, just don't worry about it. Unless you really want to know.
Wait a minute, Larry, you said that after you tell it to jump, it always executes the next line?
Yes, before it, also when it's, I'm sorry. When it sees this jump, before it goes to loop, it does this one first.
ELP is an acronym for no operation.
Yeah, no operation. No, nope. Yep. And it's like this is grayed out just to signify that it does nothing. So, push my LEDs. Now you're gonna witness the first complete program in this class that actually does something. And now you see what's going on? Just loops, right? Now if I do this, look at that. Also, I brought real hardware, not virtual. Now let's see if this program gets executed in this thing. Should have plugged it in earlier. No, I'm wasting time. This Windows will try to find drivers for it.
Are you able to change the values of the switches while programming next to it?
Oh yeah. Otherwise, what's the point? Can you imagine using microwave? Oh, I need to change the setting. Unplug, hold the switch, plug in. No, right?
So there's nothing special, right? To do that now.
Just make sure you don't fall off the memory. You loop somewhere that, so you have, even your laptop, your phone, what is it doing right now? Just looping somewhere. Just wasting energy. Okay.
It's dreaming.
Whoa. That's not good there.
I know.
So it's just like a forward-looking statement.
Now, this is what you don't see in C, right? Or Java, because it's abstracted. When you write a Java program, it quits after a certain amount of time. But your operating system never quits, right? Your operating system does have an idle loop where the CPU just executes no ops, just waiting for something to happen. That's the majority of the desktop computer. When you browse Reddit and you're just reading, right, it just does nothing. You're just wasting power, man. What the heck?
That's not wasting power.
So let's see this in action on the board. I checked this before I went here. I took the bus just to make sure it works. Hopefully it still works. Installing drivers. Okay, while we wait for that, let's move on for now. So remember this recap. Memory addressing and access, PLP instruction encoding, CPU, main memory interface, instruction and other buses, executing a program, the visualization that I made. So you see how things work, where things are stored. Memory mapped I interface makes your life easier. So everything is just a memory address, right? And then the jump instruction. Now let's move on to more control structures. And show. The human compiler. Now we're starting to connect with the higher level programming language and see how it works underneath. So now you have a notion of program doesn't just execute linearly. You can jump around, right? But is that it? So code reuse, but decision making. How do you implement decision making in your Java program?
If else.
If else, and then switch. Even in your loop, you have some conditionals, right? When to stop looping. With jump, you never stop. But you don't want to execute everything indefinitely, right? You want to actually stop at certain conditions. So that makes the CPU really a lot more useful. And then the program constructs can be realized. So now you can, if we have conditional statements, conditional support, now you can do if else, you can do switch statements, you can do for loops, while loops. But the thing is, in Java or C, it's really easy to see loops and conditionals. It's still close to our language. Oh, I have a for loop. I just loop until this happens. Oh, makes sense. The structure is still pretty clear, right? If else still makes sense. If conditional, oh, if this is met, then I execute this block. Otherwise, I do this. In assembly, it's not that obvious because you just have these lines of code, and then where's the conditional? Where's the if else? Where's the loop? So that's why we have something called flowcharts. So when you program, I have this, so usually when you code, you just pull your keyboard and start whacking at the keyboard until something works. You've done this.
Slapping on the keyboard.
Yeah, like for 5 hours and boom, done, right? Hopefully. But I always say this, when you actually work with some programs, you should not document your code. You should code your document. Have a clear idea what you're trying to write with your code, and if you need to flowchart to make sure that people know like what your code is trying to do. You don't want to just have 3 pages of code and say, hey, this is what I did. It's like, what the heck did you do? But if you have a flowchart, it's a little bit more obvious what you just wrote, or what you're trying to write, at least, if you haven't written it. So, but sometimes you don't need this. Like, there are some routine coding where you can just like, where your code is self-documented. But sometimes, many times, people need to see your code and work with it. So document it first, have a clear idea what you should do, and then code that document in whatever language you use. Right? So we saw on conditional jumps, pretty simple. The next will be branches, conditional expressions, function calls, which we'll do later. And then with all this, we can implement high-level constructs like loops, for while, if else, function calls, and data passing, and more. Right, so just with branches and conditional expressions, we can actually implement everything. Only takes 3 instructions other than jump to do it. Some architectures have tens and tens of branch instructions just to make it easier for you to do conditionals. PLP-CP only has 2. Okay, so the first one you saw, right, unconditional jump. So you have a label, and when you have the jump instruction, it jumps that label immediately. Well, after they know out. Branch on equal and branch on not equal, you have some conditions that have to be met for it to branch. And branch is not a misnomer, because if you look at the flowchart, what do these instructions do to your code? It makes another path of execution, depending on what this condition is. You said about dreaming computers. There's actually a study on like that. So in modern computers, there's this thing called branch prediction. Give me a number. How accurate do you think branch predictors are on a CPU?
82.
More than 90%. So the CPU knows when you execute the program, more than 9 out of 10 times, it guesses correctly where your program will go. There are reasons for it. It sounds like counterintuitive. So why write programs at all if it already knows what to do, right? So, anyways, so when branch on equal, you give it 2 registers, the CPU 2 registers. If those registers match, what do you think will happen? It goes to the label. Otherwise, it just falls through. Now you can kind of see how this can get really messy in the code, right? With C and Java, you can indent your code so you know like what gets executed and what's not. Assembly, no, you just jump around. That's why you should not use goto statement in C. C does have a goto statement where you can jump around the code, but it makes it really, really unreadable. Assembly, you have to do spaghetti code. There's no other way. There's no formatting. You have to follow the rules of the machine, right? So the other one is branch on non-equal, which is because sometimes you want to branch when those 2 registers are not equal. You'll see examples. Now, what if I want to do other kind of comparisons? Give me examples. What kind of comparisons do you?
Greater than, less than.
Yeah. How do we do it in PLP? So we're not that cruel. So we do have set if less than. Right. So what this instruction does, it takes 2 registers. If the first one is less than the second one, it will write 1 to the destination register. Otherwise, it will write 0. So that's how you know whether 2 values are less or not. And sometimes it's useful to compare 2's complement numbers. So we actually have instructions that are exclusively for signed numbers. So when you want to compare negative numbers or two complement numbers, you can. Correct? Question? So let's do some loops, right? So how to implement a for loop in PLP assembly? So we want to do a for loop that executes how many times? 10. So when you do a for loop, what do you need? What kind of storage do you need? The index, the counter, right? So let's have it unregistered because it fits. So register 1 is our counter. Do you think it's easier to count down or count up? Why?
You can see how many iterations it's going to count.
No, what's the advantage of doing a countdown? Yes, because we have a zero register. So when you do the compare, you're comparing to zero register. You don't have to do an extra load. If you count up to 10, that 10 has to come from somewhere, right? So you have to actually load that 10 to a register. But if you count down, you don't need your sentinel value to be loaded anywhere because you always have zero register. So let's count down. Right? So this is the I equals 10 on the initial. Make sense? Now we have 4. So what do you do in for loop? If you're counting down. That decrement, right? So how do you decrement in PLP CPU? Add IO. Right, so you take register 1, subtract 1 from it, and store it back there. So this is decrement. Some architectures have dedicated decrement and increment instructions, and it's usually pretty quick. But in PLP CPU, every instruction is 1 cycle, so you can use this to decrement. And we don't have decrement function.
I thought you said a little bit ago that you cannot indent in PLP.
You cannot. There is no notion of scope. That's just formatting.
It doesn't mean anything.
Doesn't mean anything. It's just so it makes it easier to read.
It doesn't mean anything in C either, does it?
It does. When you have your curly braces after your if statement, that code inside the curly braces only gets executed when that condition is met.
Right, but you can still indent your code with curly braces.
Yeah, the curly braces is the thing that actually controls what gets executed. Indentation just formatting. Right. Some programming languages actually use the indentation for scoping. Is that clear? In assembly, there's no notion of scoping. Everything is in scope when you see it, but you have to apply your own understanding of the program. Hey, this is not being executed. So now we have to actually see to check the condition whether we are doing another iteration or not. So what do? Do we do branch on equal or branch on non-equal at this moment? When do you branch back to 4? When it is not 0, right? And then here we just want to halt so it doesn't fall off. So this is a for loop. See how messy it looks like compared to your typical C or Java for loop? But there's structure to it, right? This is the initial condition, this is the decrement, and this is the conditional, correct? Now let's have a counter that counts how many iterations this will take. So it starts at 0, and every time there's an iteration, you add it. Just to see whether we actually get 10 iterations. Let's execute this program.
What's B and E mean?
Branch on not equal.
Oh.
What? Okay, let's look at the registers. Let's step through this. So we have loaded 10 there for the count. So keep going. Now register 1 is 0. So now it's equals 0. So it should fall through. Now you have your for loop. So
So right there, it's going to go 15, 14, 15, 14, 15 indefinitely.
indefinitely. So it loses
Where
power.
Just comes where the note statement is,
The what?
like whatever work you wanted to do, whatever you're going to write that for.
You can put something in here, right? Because as long as they don't depend on each other. So if it's an independent instruction, you execute every loop, sure. So you don't waste the space. But I don't expect anybody, like in this class, I don't expect you to optimize your program.
Just real quick, if you wanted to change that code to a 20 count for loop, what would you change?
This your initial condition.
There.
What's the purpose of your halt loop? Once your for loop is done, well, wouldn't it just stop?
Yeah. So let's execute again, right? Oops.
But really, that's not stop, right? Just keep looping on the help.
Yeah. Well, yeah. It implies that it's done and it's just there. So
So what happens if you don't have all loop again?
it starts executing unknown memories. In the simulation, it will complain. It's like, what are you doing? There's nothing here, right? What do you think happens in a real microcontroller?
Wouldn't it just continue to run through your
You're leaving your fate in the hands of God when that happens, right? Because when you boot up a computer and it's not programmed, the memory just contains random bits. Some of them may be valid instructions. Some may not be.
Can we see what it would do? Can you take off the halt, the J halt, and the NOP and run it?
Sure. No, it's a simulation. So this will fall through, right? God, Raymond, trying to break my program here.
That's how war games start.
Yeah, simulation just tells, what the heck are you doing? Stop. And if you try to run it again, it's like, no, no. So it just says no. In a real computer, on a real controller, it will just go crazy. I can show you. Let's see what happens if you want. I have a lot of big boards that we can program for fun, and I can show you what happens when you do that, Raymond. Don't do it.
Well, what I'm concerned about is I'm pretty dumb. And if there's a mistake that you've made, Tony, I make it repeatedly.
That's why you learn here to not make the mistake.
Well, what I'm saying, though, is that I would forget that
So, when you program an embedded processor, a little processor, like in a real system doesn't matter, right? Because you have the OS that takes care of this. You cannot fall off memory in OS. The worst you can do is just make it restart, because there are some safeguards, because it's dangerous, right? On a controller, when you're a savvy programmer, the first thing you do so this does not happen is this, right? So in a C program, this is what you do. And make sure whatever you write is in here. Make sense? When you program your controller in C, this is the first thing you do. When you write your program we're done with this, right? Everybody get that part? When we write program in assembly, this is what you do. Right?
I was going to ask you what the convention is to avoid that.
Yeah, you actually enclose your code with like a
So it never,
infinite loop.
you never can go into law.
Yeah. Because you're truly leaving the fate of your system to the hands of cosmic ray
That's what I
God.
was thinking, is if you could have a pre-write your little, what you got at the end of it, J halt, you could pre-write a J halt and everything you do.
That's even better because you know you get stuck somewhere. Here you can still make mistakes and actually, yeah. See, now you're learning a lot about computers, right? How machine-like they are. They're not smart. There are checks that architecture came up with, but sometimes you go so low level, it's like, this is it. It's on you. Somebody has to do it. And who like you talk about assembler. Like assembler is a program that assembles your assembly language to machine code. Somebody has to write the assembler first in machine code. Have you thought about that? 1 zeros. It's like, oh God, 1 0. So error prone. Yeah. Let's do some conditionals. Okay. Oh, I forgot to show you something. Some cool thing. Can we do conditionals today? Or do you want to just do this by yourself in the lab tomorrow? Because it's a short lab.
Yeah, let's do that.
Huh?
Yeah, let's do the short lab tomorrow.
I won't be there. Cheryl will. But I'll be online, so if you guys need me.
That way we don't have to lab.
Is he going to give us the points for the lab?
Yeah.
Is he a full-time student?
Yeah. What does it have? What does it have to do?
If we don't do so well, we can bring him pizza and probably get possible.
Cheryl.
What's his favorite kind of pizza?
For, Jennifer, you can make up for the first lab there too, because the first task is basically redo it. They'll be like, oh, we have to redo this again. We already did the code. Too bad. I just did it again in the lecture. So I basically did the first part of the lab tomorrow in the lecture. Yeah, don't fall off memory. So before we go, let's show this board.
Didn't have any jokes tonight.
I did not. Oh, boo. Serious business, man. So this is, oh, yeah, I forgot one thing. Last time when we learned, we talked about programming the CPU, the other way is to have a bootloader. So the CPU, when it comes from factory, like it's flashed, right? So it only executes that program ever, like, for example, like your whatever small devices like microphone, or not microphone, like your mouse, it has some controller, it has some program in here that you never want to patch, right? So on factory, the chip actually flash it. But sometimes you want to be able to patch your system. So there's this thing called bootloader that's always on your device, on your CPU, that executes first. What the bootloader does, it allows you to go to programming mode where you can actually update your program. If you root your cell phone, this is what's going on. So the cell phone is a bootloader that usually just launches your Android or iOS, whatever. But there's a mode where you can just execute my code, right, for patching or just bricking it. So this is the PLP CPU on hardware. Right, so this bootloader just does this while it waits for you to load a program in it. Please just work. Sometimes it takes forever to install drivers. Come on.
I can't see. Is that a watch battery in it?
What?
Is there a watch battery in it? Oh, you got to put it in the book.
Yeah, USB power. No, it's glorious. Half amp.
Black cords.
What am I doing? I'm switching to the camera so you guys can actually see it again later. The board.
What would that cost you?
120. It's a school property. Didn't cost me nothing.
Is it an Oklahoma State proprietary
No, it's
platform or something that we could
an
buy?
FPGA board, but we load the CPU design in there. Where's my mouse? Okay, there we go. Let's quickly rewrite that little.
I'm not writing it in main. Going out of bounds.
I know I'm doing.
It's nice words.
Make that look.
Hush, hush. Well, maybe give you a homework for next week. You turn to bribe me now?
That was true.
Sure. He's a good guy. Don't mess with him. Where is it?
That real easy one.
Not there. I'm trying to figure out which COM port it shows up in.
Did you get your laptop like when Windows 8 came out?
It's 2 years old. I usually have Linux installed on my computers, but sometimes it's a pain. Devices don't get supported and whatever. What's going on, man?
Good, nice manager. It's whatever done. So.
That's what I'm looking at there now.
Oh, I know you don't.
Probably not. It's not working.
It's just staring at his performance.
No, it's actually on camera. This is the PLP board. I'm trying to figure out why the UR device is not. Windows what? Is it the cable? What?
Try to import it.
Oh, broken cable is. Oh, it's actually my personal cable. There you go. Stupid cable. I hope. Just want to show you this little thing. There you go, it shows up. Port number 23. So there's a serial programmer in PLP tool. Go to program mode. Failed.
Only had 5.5.
There you go. So now I have that switch program, right? right? So these are the switches to these LEDs. You see how it copies it? So if you, well, I'm going to be here next semester. If you have taken my Compart class last year, so what we do is take the CPU design and actually implement it in this FPGA. So we have students actually code the CPU in Verilog and put it in FPGA and run their programs. So pretty cool. So it's a physical thing, not just simulation, right? We found out that when students actually see it in action, can feel it, right? It actually is more rewarding, which is true. Like, because you're so used to lectures, tests, like you don't, like fields. Like, what is this applied to? It's not up to like antennas where it's really obvious or not obvious, like what you can see it in action. Like, I can transmit data, I can transmit signals, right? Well, in fields is such a fundamental thing. Like, you can't even use that knowledge to actually do anything yet, right? So
Let's say we want to move this particle from here to over here.
particle or wave?
The charged particle. That's what we're talking about.
So anything else? Any question before I let you go?
This is probably a dumb question, but I'll ask it anyway.
There's no dumb
For
question.
your test, should we just watch your lectures on your website again, just as like a review, or because I mean we don't have homework.
Oh, we do. We just don't have it yet.
Well, oops. Will you give us a review, or?
Well, I focus more on like there are things that you need to remember, but that should be those things you can just go over my slides. If you look at the new slides, you'll know like, oh, I don't need to know this, obviously. But most of them will just be kind of like knowing how to translate from high-level program to assembly. That's the meat of this class, right? Trying to be able to capture the different intricacies and all the different concepts that connect high-level languages to assembly. So as long as you do well in your labs, I don't see any problem, and review the slides, I should see no problem. You will have a couple homework before the midterm too.
So in the test, is it going to be written only, or is it going to be a little bit of, here's a block, here's an idea,
Written
right?
and open anything, aside from collaborating.
Will you be expecting us to write you a block of code, show me a code that would do this, and write a little block?
Why do you worry so much about tests?
I don't think it does.
Programming class.
No, it's more like identifying things. I may have a C program, I'm going to ask you, okay, on this spot, what can you do? Or I can have an assembly program and ask you, okay, what am I doing here? Can you do something different? Things like that. So you have to think. You cannot memorize it. You have to know, right? You have to understand, not know. Understand. Cool. Have a good long weekend.
Now tomorrow, right?
Sherwa will be with you tomorrow.
Oh, yeah, you're gonna have a good one.
Yeah. No.
Post on your website, pizza churros.
The what? Say it again?